Hi, I'm Keenan Casey for Tuts Plus. In this lesson, we're going to be looking at the General Regression Neural Network. This is a pretty simple model that's very powerful. That's a nice introduction to neural networks. The GRNN is an instance-based method, which means we're going to use the training data that we have directly. Essentially, all a GRNN does is compute a distance-weighted average. We'll talk about how we can tune the parameter sigma and a little bit about lazy learning as well. These are the terms we need to look at first. We're going to call our input vector x, which will be components from x1 to xn. We'll have an output vector y that can be any continuous values. Training instances look like this. It's the vector of x and y combined together. Our training set is just a set of training instances. We'll have n features and m instances, that is m rows in the data set. This is what the structure of a GRNN looks like. We start with our unknown input vector x question mark. It gets sent to each of these kernels. What these are going to do is compute the similarity between the input vector and each training instance. The result of that similarity will be a number, 1 if they're the same, exactly the same, and 0 if they're very, very different. So within each of these little k's is this kernel function that accepts x sub I and x sub j, so just two input vectors. The result of that will be multiplied by the output for this training instance, and that will be passed to the summing unit here. Also, each of the similarity strings, the result of these kernels, will be passed to this adder down here, so we get the total of all of the similarity strings. We'll then divide the sum of the weighted outputs by the total sum of the weights. The result of that division will be our output y. Let's take a look at this kernel a little bit more. Really, this kernel is computing a similarity strength, how close these two vectors are to each other. And we're going to do this in a very smooth way. So we're going to follow a function that looks like this, where we've got 1 at the top if they're very similar, and 0 if they're very different from each other. How do we define this function? We're going to say that our kernel function looks like this, which is an exponential, e to a negative power. It's the difference between our two vectors squared over this value c squared, which we'll come back and talk about some more later on. Another way to look at this is this function is computing the distance between these two instances, squaring it, returning the negative of that divided by this product. We will write that as this double bar to mean the distance between x sub I and x sub j. So this is the mathematical formula for the GRNN. On the top, we're summing up the product of the similarity strength and the output. On the bottom, we're summing up all of the similarity strengths. And recall that what's inside that kernel is this formula, which we often call a Gaussian curve. Let's take a look at the pseudocode for a GRNN. What we're going to do is iterate over every training instance x sub I. For each one of those, we will compute the sum of the outputs, which is the product of similarity strength, the kernel, and the output for this particular instance x sub I. We'll also compute the sum of the weights, which is simply the sum of all of these kernels. When we're done, we'll divide the sum of the outputs by the sum of the weights. And although this is quite simple, it can work surprisingly well. Let's consider how k nearest neighbor compares with the GRNN. They actually have some very clear similarities. If we had one nearest neighbor, what we see is that really every instance has this well-defined sphere of influence around it, these polygons. In GRNN, we have this same general idea, but it's much smoother. There's a very gradual fading of the influence around each training instance, and they will also combine together. Let's talk some about that sigma value. Sigma value is the sensitivity parameter or the smoothing parameter. Depending on what value of sigma we choose for our kernel, we'll get different behavior from our GRNN. You could have it larger and make it wider, or smaller and make the kernel much narrower. If we have a large sigma, what we're doing is making the area of influence around each training instance much larger. Whereas if we had a small sigma, there's this very small area of influence. And if the unknown instances aren't very, very near to our existing training points, they won't get any contribution from that unit to its output value. Basically, if you're not very close to one of these in this x dimension, you'll get a weight of 0 because you're not at all similar to it. So we have to ask the question, how do we find sigma? And unfortunately, the answer is essentially trial and error. You can use some smart algorithms like evolutionary computation, genetic algorithms to tune this, but there's no mathematical way to know for sure this is the best sigma without trial and error. As we conclude this section, I want to talk a little bit about lazy learning. Lazy learning is a description for the kind of model that the GRNN is. Basically, it's very light on model creation, but heavy on training data. We don't do a lot of heavy lifting on the front end, but we do it whenever we have to do classification or regression. The model is cheap to create because it's mostly just all the training instances. Training is very easy, but the model is potentially very large because we have to carry around all those training instances. When we do the classification or regression, though, it's very expensive since all the training examples have to be analyzed every time. As we sum up the strengths and weaknesses of the GRNN, we note that it's very accurate, it's quick to train, and it has a good insensitivity to outliers. On the downside, we have to tune sigma, and there's no super easy way of doing that. The bigger problems, though, is that we have to carry around all of the training instances, which has very real effects on memory overhead. Got to store the whole training set in memory, and we have to compute distances to all of those different points, which may be computationally expensive as well. As we consider the GRNN, its representation is in terms of the training data set, the parameter sigma, and our kernel. We've seen it represented in this way most compactly. To evaluate the GRNN, we can use error or error squared, which is what we expect minus what is predicted, and summing up those over the data set. We could also see it as classification accuracy if we use it for classification. To optimize the GRNN, we simply have to find the best sigma through trial and error. We've looked at the GRNN, the General Regression Neural Network. It's a supervised method for classification and regression. I'm Keenan Casey for Tuts Plus. Thank you for watching.